Okay, welcome to week 6, part 2, continuing to look at AVL trees. I did make some silly syntactical errors in my code in part 1, and also some logic errors in the last couple of code examples. So I wanted to correct these errors. On slide 13, there were just a whole bunch of basically missing underscores. So I was missing an underscore in front of top and in front of value and in front of left. A whole bunch of missing underscores all over the place. And I had a stray extra self parameter in here that wasn't necessary. So I've fixed those up. Then in my update function, where we're traversing through and updating the balance factors at the nodes and also making decisions about whether to rotate or not, I was increasing my balance factor. This is for a left insertion. I was increasing my balance factor too late. So I moved that balance factor update earlier. And I also added a check so that if we are working our way from the newly added node up the list of ancestors, parent, grandparent, great-grandparent, etc., when we get to a node that has a balance factor of 0, after we've done any necessary rotations or whatever, at that point we can stop, because when we find a balance factor of 0, that means that the left and right children of that particular node have identical heights, and there's no need to go up any further. Okay. And then finally, I both corrected a typo and corrected some updating on these balance factor fields of the parent and grandparent node in this right rotate function. Okay, so that's the corrections that I've made. Onward to looking at some examples of insertions. So we're going to illustrate strictly the left side insertions, which correspond pretty directly to the example code that I showed. Now remember, we actually have 4 cases that we're going to have to worry about as far as rotations. We've got left-left, left-right, right-left, and right-right. So everything I'm showing right now is left-left insertions, and I will leave to you to implement the other things. So we start with an empty tree where the top is equal to none. When we add the value 200, then that becomes the initial node in our AVL tree. And this number over here to the right of the value is the balance factor. When we add the very first node to the tree, it has a balance factor of 0. That is, its left and right children have exactly the same height as each other, which is 0. And it's the topmost node in the tree, so there's no... so as we trace up to the parents, we're done immediately. Then, suppose we do an insertion of 190. Well, 190 is to the left of 200. So we add a new node to the left of the 200. And here are the balance factors being updated. The newly added node has a balance factor of 0 because it has no children. But as we traverse up to the ancestors, we're going to add 1 to the parent node, because now this tree is left heavy, okay? And so the balance factor for the node 200 increases to +1. Continuing on to the next example, we're going to insert 180. Okay, so we've got 200 with 190 to the left. 180 is going to be the left of the 190, and it is added with a balance factor of 0. As we traverse up the ancestors, we're going to increase 190's balance factor by 1, and we're going to increase 200's balance factor by 1. At this point, 200's balance factor is no longer valid. Remember that the balance factors have to be either -1, 0, or 1, +1. Because we found a +2, that means we have to do a right rotation on the grandparent of 180 here to eliminate that lopsidedness. All right, and so we do that. We bring the 200 down below the right of the 190. Because the 200 is now below the 190 instead of above the 190, its balance factor gets reset to 0. And similarly, the balance factor for 190 gets set to 0. The balance factor for 180 remains the 0 that it initially was. So we now have a nicely balanced tree. It is, of course, an AVL tree. All of the balance factors are either -1, 0, or 1. So that's 3 nodes. Now, when we add our next value, 170, well, 170 is less than 190, 170 is less than 180, so the new node gets added down here. And notice that as we traverse up through the ancestors, we add 1 to the 180, we add 1 to the 190, and now we're at the top of the tree, so there's no further place that we can go. All right, so in the process of adding the node 170, we have increased the balance factor for 180 and for 190, the two ancestors of 170. But since we didn't reach any value of 2, there was no rotating to be done. Now we're going to insert 160. Well, 160 is left of 190, left of 180, left of 170. And so the 160 is added down here. Its balance factor is 0. It has no children. And now we traverse up the ancestor chain. We increase the balance factor for 170 to +1. We increase the balance factor for 180 by 1, which brings that balance factor to +2. Now, because that balance factor is not legal, it's outside the range from +1, 0, or -1. Once again, we have to do a right rotation on this node, the 180. That's going to pull the 180 down below the 170, bring the 170 up below the 190 where the 180 used to be, and the 160 remains the left child of 170. 180's balance factor gets reduced by 2, and 170's balance factor gets reduced by 1. And once again, we're back to having an AVL tree. This is not perfectly balanced. Notice that at the top of the tree is left heavy, okay? We do have a +1 as the balance factor back up at the topmost node in the tree. All right, continuing on. Now we're going to add 150. All right, 150 is less than 190, less than 170, less than 160, so the 150 drops in down here. Its initial balance factor is 0. We increase its parent by 1, and its grandparent by 1, and its great-grandparent by 1. And here we discovered that the great-grandparent has got a balance factor that's not valid. Its balance factor is +2. That means we have to do a right rotation on the 190. All right, so doing a right rotation on the 190 brings the 190 down to the right of the 170. 170 is brought up in place of where 190 used to be. And notice that 150 and 160 follow 170 up. The only other change here is that 180, which used to be the right child of 170, is now modified, or relocated, I should say, to be the left child of 190. So it goes from being the right child of 170, because it's greater than 170, to being the left child of 190, because of course it's less than 190. The only balance factors that get changed in here are that the 190 gets reduced by 2 and the 170 gets reduced by 1. This is pretty well balanced, but at the 160 node, at that node, we are slightly left heavy. Okay. And so on. You can, you can follow along each time you do another insert. Here, as I said, we're sticking to doing left inserts. Each time you do another left insert, that will put a value at the bottom left-hand side of the tree, and that will probably cause some balance factor in the chain of ancestors to become a 2, and that will require you to end up doing a right rotation. Now, of course, if we were doing right side inserts, we would have to do left rotations to handle that situation. And if we were doing intermediate inserts, sort of in the middle area of the tree here, we would probably find ourselves having to do these combination left-right rotations or right-left rotations. And that is what you are going to have to develop. So I have given you working code for all of this left side insertion stuff, as well as code for displaying these AVL trees with their balance factors. And, the instructions for the homework will tell you what enhancements you need to make. It is a little picky doing this, but I don't think it's going to be too desperately hard. All right, that's it. Take care.